Hello guys, I hope you all enjoyed our introduction video. My name is Mera Abbassi. I'm a PhD student at Opuda University. My research topic is focused on automotive security. I'm a security testing engineer at Bosch since I joined the security team since the beginning of this year, and before that I was a conformance testing engineer with focus on automotive Ethernet. Before that I was also an intern working at Bosch. So I'm here to talk about security testing in automotive. Wikipedia defines security as a freedom from potential harm. So I will just assume that we all want to be from potential harm. Okay, we all know that security is important, but what's new? I'm here to say that in automotive industry, the main focus was always on safety. But I'm here to emphasize another aspect, which is security. Do we really need security in cars? Well, if we are checking these cars, we would say no. But security has been long-standing consideration in IT development, but it remained outside of the focus of our automotive industry because we didn't previously focus on connectivity. So speaking 20, 30 years ago, the biggest harm that can happen or danger that if someone can break physically into our car and steal it. But for that, we would lock our car and pray that that would not happen. But nowadays, it's different. A new generation of connected cars started with us having the ability to connect to the internet, transforming the car into rolling IoT devices. And just like any IoT device, when it's connected to the internet, it will face the same cyber security challenges that will face an IoT device. Currently, we have this semi-autonomous cars with all the fancy features that we all know, and near in the future, we will have the fully autonomous cars, so nothing is simple anymore. And these cars consist of electronic systems with subsystems called electronical control unit (ECUs). And the modern ECU is basically a small computer collecting data from attached sensors or buttons or other bus nodes, processing them and controlling attached actuators and telling the car what to do. The number of ECUs is rapidly increasing, so we can safely say now that we have more than 150 ECUs. ECUs are connected together with different types of internal bus protocols and share important vehicle state values in real time. So the critical or the important part for us here is software and the data. These protocols, you might recognize some of these like CAN, LAN, FlexRay, and Ethernet. These protocols, the important thing or the point is that they were not designed with security in mind. They are fault tolerant, they can sustain the harsh vehicle environment, but they were not designed with security features like encryption or authentication. We also have external communication like GPS or GSM. Uh, Infotainment systems that comes with the Wi-Fi, Bluetooth, USB, and we have also the connection to another car of the environment, which is starting to be implemented, which is called V2X. We also have remote access to the car, so we lock it, unlock it, start it, drive it with the remote key systems and the applications on our smartphones. So enough with the theoretical part, or let's say one last theoretical information is that we have a big number of listed automotive vulnerabilities in the CVE database by now. So we should pay attention to that. So more interesting or fun facts is this proof of concept hacks. So as you see, these two guys are Charlie Miller and Chris Woloski, and these two researchers, what they did is they took control of a Jeep Cherokee vehicle, and they have a video demonstrating that with a reporter who was driving the car at the time. It's fun. I recommend if you see that. It's interesting. So what they did is that they found a vulnerability in the head unit of the Jeep that was accessible through the internet. And after getting the code running on the head unit, they were able to reprogram the firmware of another processor on the head unit that has CAN network access. And from there, once you have CAN access, you can control steering wheel, brakes, acceleration, and leading that a lot of things can happen to the car. And this caused a lot of cars to be withdrawn. Another interesting proof of concept is the Tesla Model S. So in 2016, a security lab was also able to remotely compromise the Tesla Model S, where they took advantage of a vulnerability they found also in the infotainment system, where the web, if they could trick the user to visit a malicious website on the browser, they could exploit this vulnerability and reprogram the vehicle's gateway, and then they would get also the ability to send CAM messages and, of course, engage the brakes of the vehicle and other functions. One note that all of these are patched, so you cannot try anything on them anymore. So I would like to ask who came by car today. I can't have an answer by now, but I will assume that most of you have a car, and these cars are equipped with a lot of these advanced technologies that we mentioned before. So let me draw a picture for you that what can happen to these cars. In case you have internet, then exploitation of vulnerabilities in the communication stack can lead to severe issues such as critical ECU programming and taking control of the vehicle CAN bus, as we saw in the previous attacks. If you have mobile application, also by hacking the mobile application, an attacker can order a car to do something that it's not supposed to do, like drive it somewhere or open it. And this is also a proof of concept attack that was done by Sami Kamkar in DEF CON in 2015. Also, what can happen is that an attacker can block critical messages and cause denial of service attack, which will um, make this autonomous vehicle or semi-autonomous vehicle react inappropriately to the situation, so they cannot brake or stop or warn the driver. For the GNSS GPS, so we can replace these signals so an attacker can fool a third-party service into thinking that the vehicle is somewhere else, which can lead to accident or theft. We also have attack scenarios with physical access. So if we get access to this OBD port, then we can jeopardize or steal the car. And this port is usually used in service centers, so it is an important one. Or where the users install third-party parts to their car. Well, they want to enhance it, but these parts can jeopardize or be insecure. We also have side channel attacks. Um, it's really interesting, but we'll talk about it in the next slide. The last one is the human factor, where we jeopardize ourselves by usually, for example, installing applications from third-party sources. And these have vulnerabilities, and then that's how we can escalate and get control over a car. Side channel attacks. So this is somehow a new term. What is side channel attack? It's an attack based on side channel information. And what are these side channel information? It's the information that can be retrieved from the encryption device that is neither the plain text to be encrypted nor the ciphertext. So why are we talking about it? In the past, this encryption was straightforward. So you put plain text, you get ciphertext, and when you get both of these together, you can have an attack on them. But now it's not so simple because we have this public keys, private keys, and these informations that are hidden. So it's you cannot get it like straightforward. So with side channel analysis, we use properties of the physical system state as additional information source for cryptanalysis. Side channel attacks can be passive or active, and the active one we call fault injection. The passive attacks can involve timing information, so how long certain operations take on certain input, or power consumption, so how much power a certain operation consume on certain input. And with power consumption, we could do a differential power analysis. So based on the specific patterns with with statistical analysis, we can determine if the key block guess is correct. So how this is done is we try to guess the key, and every time we get a correct guess, then the microcontroller will take more time to process it or more power, and then we know that we guessed correctly, and then that's how we keep guessing until we get the correct key. In active or fault injection attacks, we have clock manipulation, so we insert or we remove a clock pulse. We have power glitch, um, where we insert a voltage spike, for example. So with power glitch, we need to analyze and study the power of the processor. Because we need to introduce this glitch for at the right moment and for the right amount of time. For example, as you can see here in this diagram, so the red line is where if we introduce a glitch at this specific time, then we can get the ECU to actually skip a function, but lower and upper, it will either make the ECU stop or not work or just do something else. So it needs to be analyzed and studied. This was proven in a previous SCAR conference where a group of research lab proved that an ASIL D certified automotive microcontroller were found to be vulnerable to power glitches. And ASIL D means that it is safe because this is the safety standards. So it was safe but not secure. So by introducing the glitch, they could make the ECU skip the if function and jump into the authentication, and they could get authenticated on this processor by introducing a fault injection. So the side channel attacks are getting more dangerous because it's a stepping stone to scalable to software attacks. And if you get this on a microcontroller, this can be installed in hundreds of models of cars, so you can jeopardize a lot of models. And the customer might be able to try that on their own car to know this information. And it's getting more interest in hardware attacks. So we need to start paying attention for this. So all this leads us to say that security testing should be part of testing in automotives. Um, some of these tests are coming from traditional software testing world, but with shifting focus on security goals. For example, reviews during design phase with focusing on security, reviews during implementation with focus on security, or static code analysis, where we do a collection of review techniques and automatic source code analysis and algorithm to identify that they don't have defects. On the other hand, there are security testing needs that extend beyond traditional software testing tools, for example, penetration testing and fuzzing tools that were not previously part of automotive software development, since they are specifically intended for connected systems. Penetration testing, for example, can simulate attacks from the outside communication point, replicating the threat that can happen on a car, while fuzzing um, testing, which my colleague will talk about later, can simulate the effect, for example, of a malformed input, and this can lead to software failures. In penetration testing, we do an analysis of the device structure and then the exploitation of attack points and attack vectors and exploration and exploitation of these attack points. So it's a wider way to say that our device is more secure. A lot of tests can go under the penetration test umbrella, like flooding, port scanning, vulnerability scan, but also they can be seen as separate tests. And if I will not talk about all of them, but if you are interested, we can talk about these later, or you can ask me about them at the end of the presentation. So my point is that security testing should be part of the development lifecycle. Of course, we're seeing a V model here, but in the automotive industry, it's a safety critical system, and that's why it uses V model because there is a very strong emphasis on safety and reliability, and it's well established. So by adding security over this safety model, we can guarantee safety and security. So here we have system level development at software level and development at hardware level. I will not go in details into this, but just saying that, for example, in the system context, we do a system level technical cyber security requirement for hardware and software. And after the development phase, we can do vulnerability and penetration testing on the integrated system and verification validation for the cybersecurity requirements. Also on hardware level and software level, here in the design, we can do a vulnerability analysis to identify potential vulnerabilities in the design. Also, we can do vulnerability and penetration testing on the hardware design. Same goes for software level. So at the end, we say design with security in mind. Conclusion, hacking vehicles is a real threat, and protection from that threat is not easy, but it is possible if we do uh, security testing and we make it part of the development life cycle. So security testing is a must. Secure technologies is available, but using it correctly is a challenge. So expect a constant battle. Now, my colleague will be talking about fuzzing, so I hope you also enjoy his talk. And if you have questions, then later you can ask me. Thank you for listening.
Hello, I'd like to welcome everybody. In the second part of this presentation, I'm going to talk about ECU communication fuzzing. First of all, let me introduce myself. My name is Dániel Lakatos, and I'm currently studying for my master's degree at Budapest University of Technology and Economics. I joined Robert Bosch last year. I'm currently a security engineer trainee, and I'm primarily working on stateless and stateful fuzzing and scanning. So if we are talking about testing in general, we are usually concentrating on positive test cases. This means that we define the valid or correct inputs, we also define the expected outputs for these inputs, and we check whether our application or system can provide the correct, the expected results for the inputs. However, in real life, our system will receive incorrect inputs also, and especially in case of critical systems, it does matter how incorrect input is handled because the risk is very high, people are in danger. So we need to see how our application or system will react to incorrect inputs. The problem with this is that the number of incorrect inputs is too much, basically it's infinite, so we cannot test all of them. What we can do is that we can select inputs randomly from the input space and we can try to reach as high coverage as we can. A great example which uses this approach is called fuzzing. The main idea here is that we send invalid, unexpected or random data to our target system and we are checking for overall failures such as crashes, freezes or invalid outputs. Why do we do this? Well, we have two aspects. One is robustness. It means that any input shall be handled without a software crash. This means that even if the input is not correct, even if it's coming too fast, an application in a critical system should handle this and it should not freeze or crash. Another aspect is security, because a software crash may indicate a weakness in the code. And this weakness, for example, can be a buffer overflow. And if an attacker is able to exploit this weakness, then he may take control over the vehicle and a software crash can easily become a car crash. Let me show you a short example of buffer overflow because many of the ECU software are written in a low-level language such as C or C++, where this buffer overflow is an existing problem and it's a potential risk. On this slide, you can see the frame format of a SAM-IP message, which is a commonly used Ethernet-based protocol in the automotive industry. What you can see here is pretty common in case of Ethernet, so that the length of a message is not a fixed value, but it is determined by a specific value in the header. So in the picture, you can see that in the header, there is a field called length, and it determines the true size of the message. The key here is the consistency of these two fields, so the length field value and the true size of the message. Because if they are not consistent, especially when the length is less than the true size of the packet, then a buffer overflow can occur, which an attacker can exploit, and he may take control over. Luckily, there are countermeasures against this problem, for example, fuzzing. Uh, with this method, most of these weaknesses can be identified. Let's take a look on the software components. This is what we need at minimum if we want to build fuzzing toolkits. Obviously, first of all, we need to generate messages. We can choose from a lot of different strategies. For example, we can go with the easiest approach. We can create random bytes and send them as messages to our target system. This is good for checking the input validation of our targets, but basically for nothing else. So it's not very effective because these messages won't reach deeper parts of the target application where problems are more likely to occur. So for example, a better strategy is called mutation-based data generation, where we define the valid format of the messages and we make small modifications to these correct messages. So the inputs will be partially correct and partially incorrect. So hopefully they will pass the input validation and they will cause a problem in the deeper parts of our target application. Obviously, there are a lot of other strategies as well. We also need another component to communicate with our targets, and we also need a third component which will monitor continuously our target system, and it will check whether it has been affected by the provided invalid input or not. When we are talking about fuzzing, we usually mean application or source code fuzzing. In our case, it's a little bit different because we are testing whole ECUs and not just the software, not just their components. This provides a unique challenge because these ECUs can be basically any kind of embedded systems. They come with different hardware and software, they communicate over a variety of protocols, and they also show different symptoms when they are not working as intended. It's good to test these ECUs as a whole because real functional ECUs behave differently than the software in a sandbox, so that way results can be more relevant. On the other hand, there are difficulties as well because in these cases the source code or the binary are not always available. So for example, debugging is not always possible. So in case of this protocol fuzzing, usually we have to rely on the output of the application only. We think that a software which, despite these difficulties, is able to perform fuzzing tests in an effective way has the following keywords: protocol aware, mutation based, smart, and black box. Let me go through these keywords. So this software is protocol aware because it is able to understand and modify the protocol on byte level, and it is also able to understand the connection between the different fields. It is mutation based because it creates invalid messages by modifying correct ones. It is smart because it combines good and also bad protocol elements and tries to reach deeper parts of the application. And it is black box because it tests the real hardware as a black box, not just the software in sandbox. This is good because this way there is no need for a test agent or any kind of helper software. And also there is no need for code instrumentation. Here I'd like to talk about something very important. Our main goal with sending invalid messages to our target ECU is that we'd like to discover bugs and weaknesses in the code. If we are not able to detect and misbehavior in the ECU, then basically our whole test makes no sense. So we have to try and define as many health checks as we can so that the chance to detect any kind of misbehavior is the highest. In case of automotive ECUs, we can define these health checks in many levels. So for example, we can talk about the hardware. For example, we can monitor the power consumption of an ECU, and with this, we are able to detect if an ECU reboots or restarts. But we can also go on the software level, and we can use existing diagnostic services. For example, we can read out internal error counters from the device. Let's look at our whole physical environment. On the left side, we have the software code, which we can divide into two parts, two components. We have one component which provides the test logic. We implemented this in Python. And we have another component which creates the invalid messages and also processes the replies. For example, for Ethernet, we use the SCAPI library. In the middle, you can see the test tower, which is our test equipment, which has also two parts. On one hand, it has a real-time PC, which is a high-performance computer, which communicates with the ECU and also simulates other nodes on the in-vehicular network so that the ECU can feel as if it were in a car. We also have a relay box in this test tower, which is connected to the ECU. And on one hand, it measures the power consumption of the ECU. And with this relay box, we are also able to turn on and off remotely this ECU. The setup looks like this in real life. On the left picture, you can see the ECU, which is connected to the interface. And on the right picture, you can see that the ECU is also connected to the relay box through its power cables. Now let's go back to the software side and let's see how can we build up a test case, what steps do we need. So first of all, at the beginning of a test case, we have to reset the ECU so that actions from the past won't affect the result of this actual test case. Then we have to create and send invalid messages to the ECU. We do this in groups, so-called blocks. You can see the structure of a block on the diagram with purple. After a given amount of invalid messages have been sent, we have to determine whether these messages caused a misbehavior or not. If a misbehavior is suspected, then we can reset this ECU and we can go back and perform the same actions that happened in the block. With this logic, some of the failures can be reproduced. In this example, you can see the structure of a test case. On the picture, you can see the trace of a DoIP fuzzing test. DoIP is also a commonly used protocol in the automotive industry. So at the beginning, you can see invalid messages. Basically, this is a block of fuzzed messages. As you can see, the data of these messages are pretty random. After this block, there are the health checking phase. We defined two different health checks for this specific test. On one side, we are pinging the device and we are listening for a reply. And on the other side, we are using the nature of UDP because we are sending these messages over UDP. So we send a valid UDP message to the use port and we are listening for a port unreachable message. An interesting thing to talk about is how to generate data in a smart way. It's good to have random decisions and modifications, but if everything happens randomly, maybe it's not that effective. In our case, we have two keywords for this, weights and seeding. In our software, all of the decisions and modifications happen randomly, but we are using pseudo-random numbers so that we can control this random behavior. So let me get back to the keywords. One is weights. We can define a weight value for every field. So as you can see at the bottom, the data field received a higher weight than the source port and the destination port fields. This means that the data field will be modified more often. So with weights, the random behavior can be controlled. We can modify more interesting fields with a higher probability than the less interesting ones. The other keyword is seeding. With seeding, we can reset the random number generator, and with this we can replay full action scenarios even after the end of the test manually, which is important in case of failure reproduction. So let's talk a little bit more about failure reproduction, because with this we can categorize our faults in a better way. So as I told before, we are sending invalid messages in a block, and at the end of a block, we are executing our health checks. If we don't notice any misbehavior after sending a group of messages, then we can mark the test case as passed. If we notice a problem, so that means there are failed health checks, we reset the ECU and replay the actions in the block with the help of seeding. If we don't see a problem after this, after running the health checks again, we mark this fault as a non-reproducible fault because everything happened as before, but this time we didn't experience any kind of misbehavior. However, if we are still experiencing failing health checks, we can reset the ECU again and we can replay the actions again in the block, but this time performing health checks after every sent message. With this method, we can locate messages which are harmful by themselves, and with this we can easily notice bugs like buffer overflow. It's very important to talk a few words about logging and reporting. As testers, our job is to find as many bugs in the code as we can and to forward these findings to the developer team so that they can fix these issues. The developer team will fix the issues based on our report. And if the report is not good, if the report doesn't contain all the information which is required to reproduce or locate the failure, then the developers won't be able to fix this issue. So a good fuzzing report provides the full communication log and the history of the performed actions. Let's look at a few real-life results. Let me tell you some of the few bugs and issues we found with our toolkits. For example, one of our target applications was not able to assemble incorrectly fragmented IPv4 packets. Another application was unable to assemble TCP packets which contained malformed DoIP messages, and we also experienced a performance issue. An application was receiving correct inputs, but it was receiving them with such a high bus load that it crashed. Uh, these failures are different, but all of them should be taken seriously because, as I mentioned before, a crash indicates a weakness in the code, and this weakness is potentially a vulnerability in the code, which an attacker can exploit. As a conclusion, we can say that fuzz testing is valuable. There are no perfect applications. Almost every of them contains some kind of vulnerability. And with fuzzing, many of the bugs can be found with low effort. It is also good because important test cases regarding security may be left out in other types of tests. And one thing we shouldn't forget about is that fuzzing test cases are mostly reusable with other devices compared to, for example, functional testing. So to sum up the whole presentation, the most important statement is that hacking vehicles is a real threat. And as the protection is not trivial, it's not easy, security testing is a must. Thank you for your attention, and now we are happy to answer any of your questions.